Thanks for the opportunity to give you this talk today. My name is Martina TOSCANI, and I am a postdoc researcher at Laboratoire des Infinis in Toulouse. The idea of this presentation is to introduce you what has been my research so far. In particular, during my PhD, I've been studying a particular astrophysical process that is the tidal disruption of a star, which is a treasure trove of physical information that we can observe through many different channels, and between these channels there are also gravitational waves. So I thought to organize this talk in the following way. I will start giving a sort of general context of my research, which are the motivation to study tidal disruption events. Then I will describe the basics behind the physics of TDEs so that anyone can understand what I'm talking about. And eventually I will go through the main results that I obtained with the research that I did as a PhD student so far. Okay, so let's start from the general context. When we think of astrophysics, among the most intriguing objects that we can study in this field, there are black holes. Black holes are regions of space-time where gravity is so strong that not even light can escape them. These objects are very difficult to detect, and until a few years ago, the main way to reveal their presence was through electromagnetic radiation, if there was some hot material accreting onto them, for instance, material from a stellar companion. Yet lately, this field has been rejuvenated thanks to the advent of the gravitational wave astronomy. And in particular, with gravitational waves, we have been able to see a growing number of stellar black holes, which are black holes that originate after the death of a star. And we can say that the number of stellar black holes that we have detected in the last couple of years with gravitational waves is already much higher than the number of stellar black holes detected with electromagnetic radiation. As you can see from this plot, where the blue dots are the gravitational wave detected black holes, while the purple dots are the electromagnetic detected ones. Just let me spend a few words on how we are able to see these objects. Currently on Earth, we have a network of 3 gravitational wave interferometers, which are LIGO, located in the US, Virgo, located in Italy, and lately there is also a new one, which is Kagra, located in Japan. These instruments can be thought as Michelson-Morley interferometer. In practice, they are L-shaped instruments that consist of a light source, which is the laser. Then there is a beam splitter, which is a semi-reflecting surface. Then there is the 2 arms that form an L, like the letter of the alphabet. And at the end of each arm, there is a reflecting mirror. And then there is also photodetectors. So in practice, we have that the source emits a monochromatic beam of light that encounters the beam splitter and is splitted in 2 beams. One beam travels along the horizontal arm, while the other one is reflected and travels through the vertical arm. The 2 beams encounters the mirror at the end of each arm, they are reflected back, and they merge near the beam splitter. So normally this instrument is built in such a way that the 2 arms have the same length, which is around 3-4 kilometers. For instance, for LIGO it's 4 kilometers each arm, for Virgo is 3 kilometers each arm. And if nothing has occurred, in the sense that if there is no gravitational wave has passed through the instrument, we have that the superposition pattern that is formed after the merge of the two beams is a dark fringe. But if there has been a passage of a gravitational wave, this gravitational wave causes a deviation in the length of the two arms of the instrument, which results in a deviation from the dark fringe in the superposition pattern. And this deviation is registered, is measured by the photodetector. Thus, from the measuring of this interference pattern, we can reconstruct which is the deviation of the length of the two arms of the instrument, and this information, this quantity, is proportional to the gravitational wave strain, that is the amplitude of the gravitational wave signal observed by the interferometer. Okay, so thanks to this network of ground-based detectors, so far we have seen a lot of stellar black holes, not just stellar black holes, ultra neutron star, but neutron star are not the topic of this talk. Yet, we know that there is also another class of black hole in the universe, which is actually very important from a physical point of view. There are also massive black holes, which can be divided between intermediate massive and supermassive. Intermediate mass black holes are supposed to have masses between 1,000 and 100,000 solar masses, and we expect them to be in the course of dwarf galaxies or in globular clusters. So far, there are just some observational hints that suggest the presence of this kind of object, but we have not been able to detect a population of IMBH for the universe. Instead, the situation is different if we think of supermassive black holes, which are objects with masses between 1 million and 10 billion solar masses that live in the center of large galaxies. In this case, we can distinguish between active supermassive black holes that live in galaxies that present a persistent electromagnetic activity, and quiescent supermassive black holes that instead live in galaxies that do not present this kind of activity. And for this reason, these quiescent supermassive black holes are more difficult to detect. Okay, so at this point, it is quite natural to ask why we are not able to see this massive black hole, at least so far, with gravitational waves. Well, the answer actually is quite straightforward. As a matter of fact, the ground-based detectors are operative in what we call the high frequency regime, which means that they can see the gravitational wave sky at frequency between a few hertz and around 1000 hertz. But gravitational wave signals that involve somehow massive black holes actually emit at much lower frequency. And in order to see a low frequency gravitational wave signal, we need to have an interferometer with arms long millions of kilometers, not a few kilometers like the present day interferometers. And how can we build, or where can we build such an instrument with such long arms? Well, the only way to have this kind of detector is if we go to space. The first instrument that will be launched to space and will be able to search the gravitational wave sky in the low frequency regime is LISA, the Laser Interferometer Space Antenna, that is a mission mainly planned by the European Space Agency, and that will be launched in space in 2037. It will consist of 3 spacecraft at the vertex of an equilateral triangular configuration, where the arm of this triangle will be long 4 million kilometers. And this configuration will follow the Earth along its orbit around the Sun. In particular, LISA will be sensitive between the milliards and the decayears, and thanks to this observatory, we will see for the first time massive black hole in gravitational waves. Then there are already some instruments for the future after LISA that are projected, that are already planned or at least suggested to be launched in space, which are other space-based detectors more sensitive than LISA. And between these future interferometers, there is, for instance, the SIGO and Tianjin, which are very promising. Okay, so in the upcoming future, when there will be the beginning of the gravitational wave space-based detectors, we will see massive black holes through gravitational waves. And between the events that emit gravitational waves and involves this kind of black holes, there are tidal disruption events, for short TDEs, which is my main topic of research. So let me explain what is a tidal disruption event. A TDE occurs when a star orbiting around the black hole is torn apart due to the black hole tides. So we can imagine to have a star, for simplicity, on a Keplerian orbit around the black hole that at the pericenter feels the strong interaction due to the presence of the black hole. If the stellar pericenter is smaller than a typical distance, which is called tidal radius, we have the disruption. Thus, another way to define the tidal radius is like the maximum distance that the star can have from the black hole and still be tidally disrupted. As you can see, this quantity, which is defined in this formula, depends on the stellar radius, the stellar mass, and the mass of the black hole. A very useful parameter that is introduced to describe this kind of event is the penetration factor beta, which is a dimensionless parameter defined as the ratio between the tidal radius and the stellar pericenter. Normally, this parameter can range between a minimum value, which is 1, and that we get this value when the pericenter is equal to the tidal radius, and the maximum value that we get when we have the minimum possible value for the pericenter, that normally we take equal to the spatial radius of the black hole, because it is reasonable to say that for distances, for pericenters below the spatial radius, we do not have any disruption because the star is immediately swallowed by the black hole itself. After the disruption, we expect roughly half of the stellar material to circularize around the black hole and eventually to form an accretion disk. This kind of events can actually be can be studied through different types of messengers. First of all, they are very luminous electromagnetic sources that present a characteristic bolometric light curve, which is proportional to the times to minus 5/3. So far, we have just observed the tidal disruption events in electromagnetic radiation, and in particular, from the observation, we see that this kind of events seems to be divided in two groups. We have optical tidal disruption events that are seen in optical, and X-ray TDEs, which emit mainly in X-ray, in soft X-rays. So far, we have seen 50 tidal disruption events, which are robust tidal disruption events. But if we consider also less robust candidate, the number of TDEs observed so far is roughly 100. Then we know that they can also emit from the later stages of the event. So in the same time, they also emit electromagnetic radiation. They can also emit high energy neutrinos. So far, there are some candidates, a few candidates, like between 2 and 4, if I remember well, tidal disruption events observed with astrophysical neutrinos. And eventually, they also emit gravitational waves. And in particular, we expect them to produce this kind of radiation during the whole process. While the star is approaching the pericenter and it starts to be deformed by the black hole tides, during the disruption phase, and after the circularization, after a disruption, when we have the circularization process of the stellar debris. In this talk, I will concentrate, I will focus on the gravitational wave signal produced during the disruption, because this is the strongest gravitational wave emission that we can expect from this kind of event. And in particular, this is a monochromatic gravitational wave burst that, just to give you some numbers, some quantitative information, if we consider what we call a standard tidal disruption events, which means the disruption of a sun-like star by a 1 million solar mass black hole that is located at an average distance from us of 20 megaparsec, we have that this strain is around 10 to minus 22, with a frequency around 10 to minus 4 Hertz, a bit higher. Here, I am considering that the penetration factor beta is 1, which means that I'm considering the pericenter equal to the tidal radius, that is the maximum distance from the black hole, where I still have a disruption. Instead, if I consider a white dwarf disrupted in this case by an intermediate mass black hole, I have that the gravitational wave amplitude is around the same order of magnitude as the previous case, while the frequency is a bit higher. I'm talking about the HGRs in this case. So just to illustrate what I'm talking about, in this plot, you can see that on the vertical axis, there is, let me say, the gravitational wave amplitude of the signal. And on the horizontal axis, there is the frequency in Hertz. And these curves that you can see are the sensitivity curves of LISA and other future possible space-based detectors. The two stars represent the two values that I wrote to the left of the slide. That is the strain of the main sequence stars disrupted by the supermassive black hole and the strain of the white dwarf disrupted by the intermediate mass black hole. And you see that this is for beta 1. If I increase beta, what actually happens in this plot is that this star will follow this dashed line, and this star will follow this dashed line, which is clear, which tells us that this kind of signal can actually be very promising sources for future space-based interferometers. Okay, so if we know that in the future we will have instruments to observe gravitational waves from tidal disruption events, it is important to know in advance how the signal from these events will look like and what kind of information we can extract from this signal. This was one of the main questions that I tried to address during my PhD. And in particular, to answer this question, I developed an algorithm for the calculation of the gravitational wave emission from tidal disruption events in the linear gravity approximation. And I implemented this algorithm in an already existing code, which is called Phantom. Phantom is a state-of-the-art code used for general relativistic hydrodynamic simulation. And thanks to the Lagrangian nature of this code, it is particularly well suited for simulating non-axis symmetric system like tidal disruption events. So I developed this algorithm for the derivation of the gravitational wave emission from TDEs. I put this algorithm in Phantom and I started to perform simulation to explore the different parts of the parameter space that describe tidal disruption events to see how changing different parameters can actually affect the gravitational wave signal from these sources. In particular, so far, I simulated 243 tidal disruption events, and I studied the signal resulting from this simulation. All these results are collected in an online open catalog that you can find if you are interested in this website. And the idea is to continue to update through years this catalog. Okay, so let me describe some of the results that I got with this study. First of all, let's look together what is the gravitational wave signal from the standard TDE scenario. So here you can see the two gravitational wave polarization and the gravitational wave strain associated to a main sequence stars disrupted by a static, which means not spinning, 1 million solar mass black hole at a distance of 20 megaparsec from us. Just let me say that all the simulations are done with Kerr metric, considering a Kerr metric, and in these slides, if I don't specify differently, I'm showing face-on signals. And as you can see from this plot, we have that the peak of this signal is in good agreement with the analytical estimate of the strain from a TDE, which is roughly 10 to minus 22 for this particular case. And also the duration of this signal is in good agreement with what expected from analytical estimates, 10 to 4 seconds. Then I started to investigate some trends between the gravitational wave signal and different parameters that I could change in the TDE. For instance, in this slide, I show a trend that I noticed between the spin of the black hole and the gravitational wave emission of the TDE. So on the left, in this plot, you can see I'm considering prograde orbits, which means that the star is going along its orbit in the same sense of the rotation of the black hole, which is spinning. Well, I consider three different values of the spin of the black hole. The case of a static black hole, A equals 0, A is the spin, the dimensional spin of the black hole. A equals 0.5, A equals 0.9. And you can see from this figure that, from this plot, the gravitational wave signal seems to increase for high prograde spins, seems to decrease from high prograde spin. Instead, we can observe the opposite trend in this other plot, where this time I'm considering retrograde orbits. And in this case, the gravitational wave signal seems to increase for high retrograde spins. This is the first trend that I observed from this study. Another trend that I wanted to investigate was the relation between different inclination angle of the stellar orbits with respect to the gravitational wave signal produced from the system. I expected that different inclination angle due to the spherical symmetry of the system considered should not affect the signal produced if the black hole is static, but I expect something different if the black hole is rotating, so it's not static. So you can see that in the first line, I'm considering a static black hole and different inclination angle theta for the stellar orbit. And you can see that there is all the signals are one on the top of the other. You cannot distinguish the different signals, so there is no difference. Instead, in the bottom line, I'm considering a rotating black hole, different inclination angle of the stellar orbit, and in this case on the left I'm considering penetration factor 1. In this case I'm considering penetration factor 5, which in practice means that in this case the star is closer to the black hole than in this case. And what you can see that if the star is far away enough from the black hole that the effect of the spin are not important, also in this case different inclination angle do not change the signal produced. But if the spin starts to be important and to affect the space-time around the black hole, in this case, different inclination angles change the signal produced from the system. Another trend that, for instance, I wanted to investigate was the relation between the eccentricity of the stellar orbit and the gravitational wave signal. And as you can see from this plot, the gravitational wave signal increased for higher values of the eccentricity. So, from this first study from the gravitational wave emission from individual tidal disruption events, actually we see that, at least in theory, it is possible to obtain information both on the massive black hole which is involved in the disruption, but also on the stellar dynamics. But there is also another question. There is something that we can learn from the signal of not a single TDE, but from an entire population of tidal disruption events. Well, the answer is yes, but first let me explain why it could be interesting, at least at the beginning, focusing on this on the signal from an entire population of TDE instead of the signal from an individual TDE. This plot is taken from a paper where I was one of the co-authors, and in this plot we wanted to show which is the expected number of the expected rates of tidal disruption events observed per year by different gravitational wave interferometers, plotted with respect to the signal to noise ratio. Let me say the signal to noise ratio is just a quantity which describes how high, with respect to the sensitivity curve of the instrument, our signal is. Of course, the higher it is, the better it is for detection, because it is easier to detect. And you can see from this plot that for future instruments like BBO and the SIGO, we expect to detect in gravitational waves thousands of tidal disruption events per year. But for LISA, the situation, which is the blue line, the situation is much more drastic. This actually is not telling us that it is impossible to see individual tidal disruption event in gravitational waves with LISA, but it's telling us that in order to see a single TDE with LISA, we need that it is characterized by very extreme values of the parameter involved, like a very massive star disrupted by a very massive black hole, and the star is very close to the black hole, which is a configuration that is not very likely. So for this reason, it can be interesting to see if instead it is more easy to detect the superposition of the signal of all the tidal disruption events in the universe, that is the gravitational wave background from TDEs. When I performed this calculation together with my collaborators, we decided to distinguish between two different classes of TDEs. Let me use this expression: nuclear tidal disruption events and globular tidal disruption events, where nuclear tidal disruption events are tidal disruption events of main sequence stars disrupted by supermassive black holes that stays in the core of galaxies, while globular tidal disruption events are tidal disruption events of white dwarf disrupted by intermediate mass black holes that we assume reside in globular clusters. So we performed the calculation, we did a series of hypotheses, of course, and what we obtained. Well, first we obtained that as a consequence of the impulsive nature of the gravitational wave signal from tidal disruption events that I told you is a burst, we have that this gravitational wave background for both the classes of tidal disruption events is proportional to the frequency to -1/2. And this is a distinctive feature of the gravitational wave signal of TDEs. Then we also obtained, as you can see from this plot, that while the background from nuclear tidal disruption event is in a region of the frequency interval where actually future interferometers cannot detect it because they're not sensitive enough, the situation is quite different for the background from globular TDEs that is somewhere in this green area. In particular, the precise position, the precise height of this signal in this green area depends on two main assumptions, which are the occupation fraction of intermediate mass black hole in globular clusters and the distribution of globular clusters in the galaxies. So if in the future, thanks to space-based detectors, we will be able to detect this kind of background, for the first time, we would have an information on a population of intermediate mass black hole in the universe, at least up to Redshift 3, and also some information about the globular clusters in galaxies and how they are distributed. So let me conclude this presentation with some very important points that I would like you to bring home. Okay, so first of all, the important thing to take home is that tidal disruption events emit gravitational waves in the frequency regime where future space-based detector will work. LISA will be the first detector to be launched in space, but then there will be also many others. The most important gravitational wave contribution from tidal disruption event is the burst associated to the disruption of the stars. From the detection of single tidal disruption events, we can collect information of the massive black hole involved in the disruption, but also on the stellar dynamics. Instead, from the detection of the background associated to tidal disruption events, we can build a population of black holes for the universe. Some follow-ups of this project. For instance, a project that I currently carry on is understand how the gravitational lensing can be applied to the gravitational wave emission from tidal disruption events, and also what kind of information we can extract from this type of study. But for instance, another interesting follow-up of this research will be also understand if simulating in a more realistic way stars that are tidally disrupted can actually modify the gravitational wave signal produced, or said in other terms, if the gravitational wave signal can tell us information about the internal structure of the star. And this is all from me. Thanks for your attention.